Hi, again. so, um, I'm going to try and explain spatial relationship tree and how it compares to neural networks. So let's first start off describing neural networks and their functionality and then their limitations. So, with a neural network, what it does is it tries to take a pattern and convert it to points in a nth dimensional space, and TensorFlow has a good visualization of these data points in a three-dimensional space. And what a neural network is trying to do is plot the image, the pattern that it sees, and if you give it a bunch of patterns, it plots all the patterns that it sees, and it tries to find the similarities between those patterns. And so if you're looking at a dog, it tries to find that shape of, and we're going to stick with the dog blueberry muffin problem. It tries to look for the shape of the two round eyes and the round nose, and then a jaw line, if you will. And it tries to look for that shape, and it says, or all the images that it's being shown that are dogs, that are labeled as dogs, they exist over here in this space. And then you say these are not dogs, and it creates like a dot pattern of a plot of those images over here. And it can find a line that's between, it can find a line between these two graphed images. That's linearly separable. Linearly being, it's nth dimensional space, but it's linearly separable. So the idea is that if I build a graph, a neural network, I guess it's a network as opposed to a graph, but anyway, I build a neural network big enough that it can find the linearly separable space for a given set of images. The problem is, though, that the math itself starts to break down at larger and larger and larger graphs. I mean, it's either not computationally possible, or you start getting errors, and the errors propagate through the graph. One of the big issues that I constantly run into is divide by zero just happens somewhere randomly in the graph. it's like okay, that just crashed that whole model. And you either fix it by giving it more or less data. You try to find the data point that's causing the divide by zero, and you remove that data, and then it becomes stable again. Or you try to find a graph shape or a network shape that doesn't cause the divide by zero. And it's a very complicated, long, drawn-out process. I mean, they keep quoting. They love to quote, which I think is hilarious. It's like the opposite of good, but they love to quote. It took 230,000 years of processing time to get to a solution that works, and it's like that's a bad thing, not a good thing. But they like to quote it as a good thing. So we can break this down and make it more less computationally intensive by saying, okay, well, let's create a network that can figure out what dogs are. Let's create a network that can figure out what fur is. Let's create a network that can figure out what bread is. Let's create a network that can say this is a blueberry muffin. And then we can create an architecture above that, whether it's based on neural networks or not. I mean, this is exactly how AlphaStar works. AlphaStar, broke down all the strategies inside of StarCraft into their own little networks. Instead of trying to have one neural network try and figure them all out, they have a bunch of little networks focusing on just that idea. And that's fine, but that also points to the fact that neural networks are only good for pattern matching. They only can identify one specific type of pattern. You try to get it to understand patterns across domains, or patterns across, or similar patterns but are different. You start running into these errors of divide by zero, or unable to linearly separate the the two so your graph isn't big enough. And so I thought about this a lot. And in 2010, 2009, somewhere around there, I made that realization that neural networks are just not going to solve the complex mental ability that humans have. It's just stuck on this concept of pattern matching as opposed to being able to reason or understand a concept as opposed to a pattern. So a concept is car. Well, what defines a car? So a neural network can say that this is a car, that's a car. But then you try to say, well, what's a bird? And then the neural network's like, I don't know. I know what a car is. So it can pattern match a car and understand the concept of a car, but it can't understand multiple concepts. And so I thought about that a lot, and there's this concept called memory palace. So let's say the word orange. If you start thinking about orange and you see what's related in your brain as to what's related to orange, you have, like the actual food, orange. And then you have maybe a car that's orange that pops into your head. There's a line of tools that are orange. They like to use orange. So let's go to cars. So I say the word car, and then, a bunch of cars pop into your head, and you start seeing, your daily driver is probably the thing that pops into your head the first. And then maybe the car that you dream about buying is another thing that pops in your head. So how are these actually connected? How are these actually related? And in a neural network, it doesn't work that way at all. A neural network just sees, like bits of data. I mean, if you've seen the Picasso paintings, if you will, of the extracted data in the middle of a neural network, it's a mess. And it's a mess because the neural network doesn't understand what this stuff is. And it's not organized in any kind of sense of the word. It's not put into a structural hierarchy. It's not put into any kind of semblance of relationship patterns. It's just kind of blurred into there, and it says, maybe something works. And so I come back to this concept of memory palace, which is an actual thing that people use to train their brain to organize information, to be able to retrieve information a lot more easily from their brain. And it's based on relationships. It's, I associate a jewelry box with the memories of this person that I used to know. And so I only have to remember the memory box, and I can easily access the memories associated with that. And that's because I've trained my brain to say memory box is related to this person. And so thinking along those lines, I started trying to figure out how can I create an algorithm that works in the same way. And I came up with spatial relationship tree. Now, I've had this notion of spatial relationship tree probably since the beginning of when I started thinking about this. Probably back in 2002 or so. And so the idea is that the graph itself organizes itself in a way that structures the data to be relationally oriented. And so if it hears the word orange, it highlights a part of graph. If it hears the word red, it highlights a different part of the graph. There's overlap because there's similarity, and that means it's not linearly separable. None of this is linearly separable. It relies on the fact that this information has overlap. It's a fundamental need for this graph to work, that the information has to overlap. And so allowing the overlap to occur means that I can have one aspect of the word orange. I don't know what word is similar to orange. So let's say car versus cat. Car and cat is similar. There's a lot of overlap in those two words. But my graph allows it to say, okay, well, there is some differences, and these are what the differences are. And based on that model, I can then converge everything into the same graph. I can say that the sound orange exists over here, and it highlighted this part of the graph. and I can say the picture of a car highlighted this graph. And then we get into the concept of temporal knowledge. And due to the fact that they occur at the same time, I'm seeing an orange car and I hear the word orange. They happen at the same time. They're activating in the graph at the same time. They become connected ideas. They become connected concepts. They become spatially related. And that's the idea. That's the notion right there, is that not only do I have a graph that can see both the similarities in things, but it can also see the differences in things, and it can connect based on time relationships, say that these things are occurring at the same time. And then on top of that, I also have another aspect to my algorithm that does reinforcement, and it also does degradation. And so over time, if something keeps occurring at the same time as something else, let's say orange car, I keep seeing an orange car, I keep hearing the word orange, or I have conflicting information, I see an orange car but somebody says it's blue, and whichever one is stronger, that reinforces the idea, the connected relationship. And so that's the idea behind my algorithm. It's both, it solves two problems. One, it's actually really fast. I've been able to optimize it to make it pretty fast. And two, there's no actual math going on. I mean, there is the reinforcement math, that's math, if you will. So that reinforcement is a mathematical calculation, but it's just a simple sum of the activations. It's not complex calculation. There's no matrix math going on like there is in neural networks. The other thing is that not only can my graph handle complex ideas, but it can handle simplistic ideas. One of the other issues I had with neural networks is that I was trying to get it to linearly separate three input values. And it's like, it can't do that. I mean, it can, but it couldn't do it on a dynamic scale. It couldn't handle the small and handle the big at the same time. It's back to, it can only handle one pattern at a time. It's like, okay, that's the pattern I can handle. I can deal with 3 inputs. I can't switch it over and say, well, deal with 100 input. Or now that you're dealing with the 3 inputs, let's add another 3 input network and make you guys work together. I couldn't make that happen. Where in my algorithm, it directly takes 3 inputs and says, okay, I could do this with these 3 inputs. And then I can expand that and say, here's another 3 inputs. And it'll figure it out. 3 inputs are basically RGB, so pixels. So I was trying to break down a neural network to be able to identify 1 pixel, and it just didn't work. It wasn't functionally capable. So there's a sweet spot with neural networks. You go too far to one side, i.e. small, and it doesn't work. You go too far to the other side, large networks, and they become computationally error prone. My algorithm can handle the small. I mean, my first test case is 4 inputs with 2 states, each input28 2 states, and it works. It works perfectly fine with that. And then I stepped it up to character recognition, which is 28 by 28 pixels with 0 to 255 values. And you times all that together and it's like millions. I don't know exactly how many it is, but it's like millions. And it doesn't linearly separate. It mashes the stuff together and says, well, this is similar, but it's a little different. This is similar, but this is a little different. That's how my graph works. And so I hope this explanation is informative and helps with the understanding of what my algorithm is. As usual, if you have questions, feel free to post in the comments. I'll try and answer them the best that I can. I suck at communicating and all that jazz. And thanks for watching. Till next time.